Alright, so today we are going to look at what's called the derivative function. Now we've already kind of found the derivative, but we found the derivative in a specific sense. And here's what I mean by that is we have our first example, which says determine the slope of the tangent line to y equals x squared at any point x. Alright, so now we have found in our last unit, and we did this in advanced functions, we found the slope of a tangent line at some point of x. But now I'm just finding it at any point x. So what that means is that we use our definition of a limit again. So a limit as approaches h, or sorry, the limit as h approaches 0. We have our function. Now normally we have this x plus h. Normally we had the x value. Could be 1, could be 2, could be something else. Minus f of x divided by h. Now because we're finding this function at any point x, I'm not going to substitute in a number for x. But I am going to use my definition. So I've picked a simple function here, y equals x squared, to use as an example. Alright? And so, by definition, we have the limit as h approaches 0. Alright, x squared. So f of x plus h, I'm going to have a x plus h squared. Minus f of x, which again, our function there is x squared. And again, divided by h. Alright, continuing on. Again, it's important for those of you on the CAT to write down the limit as h approaches 0 each and every time. Alright, so again, doing a binomial squared, saw a couple people had issues with that. Overall though, you guys were pretty good on that the last CAT. But again, I square the first term, that's an x squared. Then I go 2 times h times x, which is going to be 2 times h times x, I guess. And then a minus x squared. Oh, forgot, sorry. My last term there, before I get to the x squared, is I forgot to square my last term, which is the h. So I have a plus h squared minus x squared, all divided by h. Alright, now we have an x squared and a minus x squared. Well, those terms are going to cancel each other out, adding one, subtracting the other. And so now I have the limit as h approaches 0. I have my 2hx plus h squared divided by h. Now, just like we did before, the whole goal here is to get rid of that h in the denominator so that I can actually substitute in that h is 0. But again, I can't do it because the denominator would be make it undefined. But I can factor out an h in each one. Alright, so it's the limit as h approaches 0. Factor out an h, so I got an h in front. I'm going to have a 2x here. And a plus h, because one h is gone. And then, of course, I've got my h down in the denominator. Now, the h in the numerator and the h in the denominator, of course, will divide each other out, which now means that I'm going to be able to sub in x equals 0 into my limit, because now my denominator would be 0. And, well, that makes that h 0, and I'm just left with 2x. And so, what we have now is this y equals 2x. This is the equation to find the slope of the tangent at any point x for this function y equals x squared. And the reason we do that now is that we have this equation, which we call the derivative, we'll get to that, is that, so now in b, when it says find the slope of the tangent at x equals 2, x equals negative 3, now I don't have to do this limit twice. I only have to do it once with just an x, and now I can find the slope of the tangent line at multiple points of x. Again, not just at one, so we don't have to keep doing that limit thing all over again. Alright, so in this case, find the slope of the tangent line at x equals 2. Well, there's the equation, y equals 2x, and at x equals 2, Well, I substitute that, well, the slope of the tangent is just 4. 2 times 2. No problem. Again, didn't have to do all this with the x value of 2. Because then in, so that was B, and then in C, it says, well, x is equal to -3. Find the slope of the tangent line at x equals -3. Well, again, I'm going to use the derivative as we call it. Whoops. And I can substitute in that -3, and of course, then the slope is -6. Again, saves us having to go through the limit again. And so, what I'm trying to say here is the therefore statement at the bottom here is, therefore, the derivative of a function, what we just found here, is the equation to find the slope of the tangent line at any point x. Not just a specific point x, a special point, any point x. Now the symbols for the derivative, there are several depending on how your equation is represented. If you have an equation of f of x, the derivative looks like this, just an f with a little comma, f of x. A lot of times you'll see if it's y equals, then you'll get y prime as it's called, so y with a comma. Or what you might get is you could get dy dx. Sometimes they say die y dx. I don't know why. I think that d is actually a Greek letter because it's a Greek mathematician. I think it came up with this. But what that dy dx means is take the derivative of your function y and it's got an x in it. That's all that means. All right, so we get to example 2. Find the derivative of s of t equals the square root of t. All right, so I'm just going to find the derivative. So that means I'm going to find the equation for the slope of the tangent at any point x. So again, I'm going to use my limit formula. The limit as h approaches 0. Again, I'm going to use my definition where s of t plus h, so I'm going to have the square root of t plus h minus s of t, which is just the square root of t, divided by h. Now again, this is a type of example we did in our first unit here, where again I have a problem where my denominator is going to be 0, and that makes that function undefined. I can't find the limit. But I'm going to again multiply by the conjugate, as we call it. So I'm going to have a t plus h. That's a minus sign, so we get a plus the square root of t. And again, I'm not changing the way this function, I'm only changing the way it looks, so I'm going to have one in the denominator here. Because again, these two would just divide each other out and it would be a 1. Alright, so again, now we find the limit as h approaches 0. My numerator, let's see, again, we have two binomials here multiplying each other, and so again I'm going to use FOIL. The first one's the square root of t plus h times the square root of t plus h. Well, you just get a t plus h. And then again with FOIL, the outside and the inside ones cancel each other out. That's why we're doing this. And then we have minus the square root of t times the square root of t, which is just a t. Alright, and then our numerator, we're going to have our h times the square root of t plus h plus the square root of t. Alright, so let's see here. Well, we do have some simplifying going on here, is these t's cancel each other out because we have a t minus t. And now all I have is an h in the numerator, and I have all this in the denominator. Well, just because I don't want to write it out again, these two h's, the h in the numerator and the h in the denominator, will divide each other out. So now all I have is 1 in my numerator. Alright, so now I've got the limit as h approaches 0. Just a 1 in the denominator now. That h is gone, so then I've got the square root of t plus h plus the square root of t. And now what we have here is I can plug in a 0 for h, because that will not make my denominator equal to 0. And so I end up with 1 divided by the square root of t plus the square root of t. And so, therefore, I want to find the derivative of s of t, which notation I'd have s comma t is going to equal 1 over, and well, I have a square root of t plus the square root of t. Well, I got 2 of them. So 2 square roots of t. And so now I can find the slope of the tangent line to this function at any point of t this time out. All right, so there's our derivative. All right, let's try a couple more here. F of x. Find the derivative of f of x if f of x is equal to 1 over x. All right, so that's that reciprocal function we're looking at. All right, our not a reciprocal, our reciprocal function. All right, so again, I'm going to use my limit here. I'm going to put a little divider here, just keep things straight. So I've got the limit as, again, h approaches 0. And our function now is 1 over x. So again, my denominator here is going to be the h. But I'm going to have f of 1 over x plus h. Whoops, minus f of x, which is 1 over x. There we go. All right, now, the problem we've had here before is we've got a numerator, we've got that fraction inside of a fraction again. All right, so the first thing I want to do is, again, simplify my numerator. And to do that, I'm going to have to come up with a common denominator, which means I'm going to have to multiply both terms here. So my first term, I'm going to need to multiply x on the top and x on the bottom. And then on my second term here, I'm going to have to multiply the top by x plus h and the bottom by x plus h, so that I get a common denominator of x times x plus h. All right, so let's see here. So now I've got the limit as h approaches 0. Let's see here. So again, we'll draw a big sign there. So I still got that h as my numerator there, but whoops. Let's try to keep it clean here. All right, so again, my common denominator is now x plus h times x. All right, on the top I'm going to have an x, and then minus 1 times x is a minus x, and then minus 1 times h, which is a minus h. I saw that a few people got stung by that before. With this minus sign, means it goes across both the x and the h. All right, and then of course that's all divided by h. All right, so let's see here, continuing on. Well, x minus x, those cancel each other out. So what do I got here now? I've got the limit as h approaches 0. In the top now I just have a minus h divided by a x times x plus h, just make it a little cleaner, and again divided by h. Now this is where I'm going to use that trick again. With when you have I'm going to create a fraction divided by a fraction. All right, and I'm going to do that so that again that I can simplify things by just inverting and multiplying. And so really I'm going to get equals the limit as h approaches 0. Here's my first fraction, the negative h divided by x times x plus h. All right, and then again, whoops, I want to make that clear, that's multiplying there. Multiplied by, again, I'm inverting and multiplying, so h over 1 becomes 1 over h. And, well, I'm lucky now that I have an h in the numerator, h in the denominator, so those divide each other out. So I got a negative 1 there now because that minus sign. And so, let's see, get down here. So now I have the limit as h approaches 0. Negative 1 times 1 is negative 1. And then in my denominator, I'm just going to have an x times an x plus h. And now, of course, I've achieved my goal of having a denominator that's not going to be 0 when I plug in that h value. It's in fact going to be -1. Let's see, I have x, and then I add h is 0, so x times x is x squared. And so if I'm finding the derivative, which is f prime, or the derivative of x that has multiple names, it's equal to -1 over x squared. And again, the derivative represents the equation to find the slope of the tangent line at any point x. And so again, I could plug in multiple points and not have to do this limit thing over and over again. All right. Let's, we're on example what, 4 here? I haven't even looked yet. Example 4, oh, okay, a little bit different one. All right, so I'm just going to have to clean this off. Feel free to write any questions in the chat if you do have them. Or speak up, I can hear you too. I think I can anyways. All right. All right, next up, what are we going to go with here? Find the derivative. Make sure that's nice and dry. Example 4. Find the derivative. Use a good pen. Of the absolute value. It's always tricky. Right, absolute value. Find the absolute value, or find f of x. F prime x if f of x is equal to the absolute value of x. Alright, so, oh, and then it says, well, we'll get to that at x equals 0. So we actually do have a specific area this time out, alright, or a specific value. But again, I'm going to find the limit, use my definition once again. As h approaches 0, we have the absolute value function, so we're going to have the absolute value of x plus h minus the absolute value of x. And again, that's going to be divided by h. Alright, so let's see here. Oh, I actually know the x value. It's 0. So, alright, well, the limit as h approaches 0. Well, I'm going to plug in a x value of 0, so this time we're actually finding the slope of the tangent line at a specific point. And so I'm going to have just the absolute value of h minus 0. So that's all that's going to be on top. And again, divided by h. Now, the problem here is that the absolute value, again, is a piecewise function. So we're actually going to have a two-sided limit here, which is weird. Alright, so if I look at the limit as h approaches 0, alright, from the left-hand side, now, from the left-hand side of the absolute value at 0, right, that value is always going to be negative. And so the absolute value flips it to a positive. And so our function would be negative h divided by h. Alright, so again, with that two-sided limit, because the absolute value flips things back to positive, when you're left of 0, which is all the negative numbers, your h is going to be negative, and so the absolute value needs a negative sign there to, well, flip it back to positive. And now in this limit, well, we're also going to look at the right-handed limit. How's that? As h approaches 0 from the right-hand side. And again, we're going to have this h in the denominator. That's not changing. But from the right-hand side of h, which is, again, 0, all the values are already positive, so it's just an h. And so because what we have here is, well, h divided by h is just a -1. I don't even substitute in a value there. The h's cross each other off. So the limit is -1. And these h's divide each other out, and we just get a 1. And so in this case, the limit, because again, this was key in our last culminating assessment task, because the left-handed limit and the right-handed limit are not equal, the limit, as h approaches 0, for our absolute value of h divided by h, does not exist at x equals 0. Doesn't happen. And here's what's happening, in fact, is that our graph of the absolute value function looks like this. And so what is the slope of the tangent line at x equals 0? That's right here at this point. Well, it's all over the place because there's not just a nice slope there because it's a jagged point. Everywhere else, we're going to be able to find the slope. No problem. But at 0, that's a problem. And in fact, we can have a lot of different situations. So because f of x does not, the limit does not exist at that point, means you can't find the derivative of that point because there's multiple slopes, multiple different slopes that you could say, but there isn't just one. And so in fact, it's not differentiable just at 0. Now other situations where other times, because this is going to be part of our graphing as we move along, learning how to graph any equation, where our derivative does not exist, is you get like this, number 1. So it's always when there's something funny happening. You can get kind of a funny looking V or something like that, or upside down. And at this point, that's called a cusp. So it's similar to our absolute value, it's just there's a curve instead of straight lines. But again, you can't find the slope of the tangent at that one point because there's no slope there. You can't determine one single slope. Another situation where you get, let's see, a graph that goes in an S shape, kind of a weird S. There we go. What was that? I don't even know if that's an S, but so at this point right here, because what you have is a vertical tangent at that point. And vertical means straight up and down, and again, the slope of a tangent, if you have a vertical line, well, it's undefined because you have no run. It's just straight up, no run, all rise. And again, the formula for slope, rise over run, well, if your run is 0, your slope is undefined. So that's another problem. And then number 3, well, this is something we've had before, is when, and this was on our first CAT, is, I think I almost had this type of question, something like that, where you have jump discontinuity. Is another situation that at this point you cannot find the slope of a tangent because the graph jumps at that spot. And so again, that's a spot, only the spot where you could not find the derivative. Alright, so there is times or spots or functions where have spots where you actually can't find the derivative at that particular spot. Because again, we just tried to find the derivative at a specific value. Before, we were just finding the derivative, which is just an equation for, again, to find the slope of the tangent at any point x. Alright, and let's see here. Let's see, going to try one more here. Example number 5. Get rid of these guys. Alright, now the next one's a little more packed, our last one here, example number 5, where it says, let's see here, determine the equation of the normal line to the curve y equals x over x plus 1 at x equals 2. You know what, we're not going to get into that, so I'm going to stop it.